In this lab, I will represent gravity through the action of dropping a ball from rest. I will analyze a video of this experiment and compare this data with that from Python. Half of the Python data will reflect gravity in an instance involving zero drag, and the second half will show what actually happened in the experiment. Here is the video I analyzed in Tracker. I used a calibration stick to show Tracker that the diameter of the ball was 7 centimeters, or 0.07 meters. I then moved the origin to the center of the ball's original mass before it was dropped. Here is the video itself. Before I could create a computational model, I had to first compute what I would enter into the Python code. These are my computations for the gravity model with no drag force. The formula I used for gravity was -mg, where g on Earth's surface is 9.8, and the mass of the ball was represented by m. These are the computations for gravity with drag. I used the formula for drag of -kv, which is the same as -1 times the drag coefficient, which was 0.47, times the average velocity. Here is my Python code for the case of no drag force. Here, as you can see, the only direction for the net force is in the -y direction. This is because, in this case, we are not studying drag and the only force is down. This is different than from Lab 1, because in Lab 1 we were studying constant velocity, so the net force would be 0 in that case. But it is not so here. In the other places which required new input values, I simply inputted the correct ones, which are shown in Tracker, because this was the exact same steps as we did in Lab 1. Now, here is the model of showing gravity and drag. As you can see, the net force has a direction in the -x direction and in the -y direction. This difference in net force is the only difference between the two sets of code. And now, here is the model for the model without drag, and now with drag and gravity. As you can see, there is almost no difference. Finally, I compiled all my data into a single graph. Here it is. As you can see, there is no distinguishable difference between the two sets of data from Python. However, there is a large and clear difference between these sets of data and the experimental positions collected from Tracker. There could be several reasons for this difference. In the video I analyzed in Tracker, the ball spun considerably in the -x direction. Also, the flames were blurry, so I may have miscalculated the center of mass of the ball in each frame. What if the ball was initially thrown downward? Would the terminal velocity in this case differ from that of when the ball was dropped? Terminal velocity is when the net force acting on the ball is 0. The terminal velocity would be the same, but the time intervals would be different. When the ball was thrown, it already had an extra force acting on it. So in order to reach a net force of 0, it would have to slow down as the drag increased exponentially. As a result, the ball would reach terminal velocity faster when it was thrown than had it been dropped. The dropped ball would have to increase in speed in order to reach a net force of 0 and therefore terminal velocity.